Example 7. Students are pulling a 2 kilogram friction block along a rough but level surface. In one case, it's determined that the position of the block as a function of time can be modeled by S of t equals 0.3 t cubed minus 0.1 t squared plus 0.2 t. Part A. Find a function for the speed, which is the velocity, at which the block is moving on average during the first 3 seconds. When we talk about a block moving on average, that means we're looking for the average rate of change, and for the first 3 seconds means we're looking between 0 and 3. So we're going to do S of 3 minus S of 0 divided by 3 minus 0. So if we take 3 and we plug it into the above function, we're going to get 7.8 minus, and if we plug in 0, we get 0, all divided by 3. So when we plug that into the calculator, we're going to get 2.6. Now remember that S of t, right, is going to give us the position, and time is going to give us seconds. So our formulas didn't help us when we still had to calculate the average rate of change. However, in part B, when we're looking for the velocity at time equals 2, we're looking for an instantaneous rate of change. So here we can apply our formulas because now we can talk about the velocity, which is the derivative of position. So here we're going to take the derivative of position, and we're going to get, so the 3 is going to come down and multiply the 0.3. So we get 0.9 t squared minus, now 2 comes down to multiply the 0.1, so 0.2 t to the 1 plus the derivative of 0.2 t is 0.2. So we have a formula now for the derivative. We didn't have to approximate it really, really close to 2 by using things like 1.99, 2.01. Instead, we get the derivative function, and then we can calculate the velocity by just plugging in a 2 into the derivative function. So when we plug in 2, we'll crunch those numbers, and we're going to get 3.4. So we were able to find an exact velocity rather than an approximated one because we now have a formula that lets us do polynomial derivatives. Part C. Find a function for acceleration as a function of time. So as a reminder, acceleration is the derivative of velocity, or what's called the second derivative of position. So here, if we take the next derivative, which is the derivative of velocity, we can find the function for acceleration. So the 2 will come down and multiply the 0.9, giving me 1.8 t. Now here we have minus 0.2 t, so the derivative is minus 0.2, and then the derivative of the 0.2 that's by itself is just 0 because that's a constant. So now we have a function for the acceleration. Having this is very powerful because we could compute the derivative or the velocity at any time, as well as the acceleration at any time, because now we have a way to find those formulas. Example 8. Find the equation of the tangent line to f of x equals x squared minus 4x plus 1 at x equals 3. So let's remember what our derivative tells us. The derivative is going to give us the slope of the tangent line at a point. So that's part of what we need to find the equation of the tangent line. The other thing that you need to get the equation of a line, if you have a slope, is a point that's on that line. Well, the point at x equals 3 is the one point that's shared by both the tangent line and the function. So in order to figure out this problem, we need two things to put together the equation of the tangent line. We need f of 3 and we need f prime of 3. F of 3 is going to give us the point that's shared between the tangent line and the function. So f of 3 means I'm going to take 3 and I'm going to plug it into my given function. So 3 squared minus 4 times 3 plus 1. So that's 9 minus 12 plus 1, which is going to give me negative 2. So that means f of 3 equals negative 2, or we can write the coordinate point here, 3 comma negative 2. That's the point where the tangent line touches. Now, if we find the derivative, we'll be able to find the slope of the tangent line at 3. So over here, we'll find the derivative of our function using our rules here. So the 2 comes down, and we subtract 1 from the power, minus the derivative of 4x is 4, and the derivative of 1 is 0 because 1 is a constant. So f prime of 3 means that I'm plugging a 3 into my function here. So I have 2 times 3 minus 4. So 2 times 3 is 6. 6 minus 4 is going to give me 2. So remember, that's the slope of the tangent line, right? The derivative tells us the slope of the tangent line. So now I need to take my point, 3 comma negative 2, and my slope, 2, and put that together to find the equation of the line. So the equation of a line can be written as y equals mx plus b, or y minus y1 equals m times x minus x1. Either is fine, but I'm going to use the y equals mx plus b form to figure out this problem because that's the way I generally do it. If you want to use the other form, that's fine as well. So here, my slope is 2, so I have y equals 2x plus b. Now to find my b, that's why I need my point, because I need to plug in the point to be able to solve for b. So I'm plugging in a 3 for x and a negative 2 for y. So that leaves me with just a b, and everything else is a number. So 2 times 3 is 6. So I'm going to subtract 6 from both sides, and that's going to tell me that b equals negative 8. So once I know what b is, I can put everything together to get the final equation of my line. My slope was 2, so I have y equals 2x minus 8. So that's the equation of my tangent line at this point. So this again is at the point 3 comma negative 2, and the equation of the tangent line is 2x minus 8.